Hello everyone, welcome to this additional topic. So in this video, I would like to review a few topics that actually we went through in class. So first one is the partial derivative and continuous function and what is the limit. So we'll talk about the derivative, which measures the sensitivity of y with respect to x. So in general, we can express y is a function of x, right? Meaning x goes through f as a transformation or a mapping, and then get us y as output. Now, so this is a function we have, and it happens that the function may be having multiple variables. For example, in the case of the volume of cuboid, for example, and we have the volume calculus pi r square h, right? H is the height, r is radius. So we can express this as a function of r and h. So now we have two independent variables, r and h. So these are our inputs. So we have one r, one h, and then we can calculate the v, the output. So the partial derivative measures the sensitivity of v, the volume, with respect to each of the input variables. So now naturally we have two partial derivatives, dv over dr and dv over dh, right? So these are two partial derivatives, and they jointly form the so-called gradients. So this is what we call the gradients. And if it's, because now this is two elements. So if it's one-dimensional, for example, if it's dy over dx, there's only one input x, then the gradient is just the derivative itself. So in this case, now how do we calculate the partial derivative? We can just use the derivative rule to calculate the derivative. So this requires, when we're calculating, for example, the sensitivity of volume with respect to the radius, then we're actually treating all the other variables as constant. Now, when they are constants, we can just, for example, express v as pi h multiply r square and over dr. So now we can actually move pi h outside because they stay as a constant. We have dr square over dr. Now, when we take the partial derivative of r square, now it's the result will be 2r based on the rule of taking the derivative of power function. So the rule is that x to the power of n. If we take the derivative, now the result will be n multiply x to the power of n minus 1. So this is the rule we're using. So now the result will be 2 pi h r. Similarly, we can say now pi r square stay as a constant because now h changes. It's the changing variable, and we're taking derivative with respect to h. So now we move that outside. dh over dh now itself just 1 because, so this is pi r square, right? So pi r square because now h itself derivative is going to be 1. Right? Why? Because now 1 moves, it's going to be 1 multiply h1 minus 1, right? Which is just 0. And anything to the power of 0 is just 1. So this becomes 1. All right. So this is the partial derivative. And basically what it means is that given a unit change in r, this is my change in v. And given my unit change in h, this is my change in corresponding v as well. So basically, if we are asked the question, which one to invest in, whether the radius or the height, right? Because both of them impacts my volume. And given a limited budget, I want to say which one increases my volume more, right? So the way we can answer this question is by getting the derivative, because this is how each of the variables impacts the outcome, the volume, right? So basically, if, for example, this is bigger, right? So meaning the volume is more sensitive to r, the radius, then we should invest in the radius. Similarly, if height has a bigger sensitivity, a bigger partial derivative, then we should invest in h. All right, so that's one way to look at it. We can also look at it from another perspective, which is to argue based on the differential. Right? So the differential is basically the dv, right? dv is our differential. What it means? So d stands for differential. What it means is that it's basically a change in volume, right? So how big is the change? And we need to concern it, we need to associate it with the concept of a limit. Basically, the underlying assumption is that when, for example, when r, right, goes to zero, meaning we have a very, very small change in radius, right? How much change in volume will that lead to? So basically, that's what differential means. The change in the corresponding variable, giving a very small change in the radius. All right. So now this is actually can be decomposed into two things. So we have our original radius, and we have the new radius, which is r plus dr. Right. So we have a very slight change in the radius. Now, how does that impact my radius? So the change in radius is going to be the new volume, which is just plug in the formula, r plus dr square h minus the previous volume, which is pi r square h. All right, so we can just proceed by expanding it out. Let me just put it here. So we have r square plus 2r dr, then plus dr square. It's good to add a parenthesis so that it's more clear. And parenthesis, we have h minus pi r square h. So keep moving on. We just multiply by h inside each element. So it's gonna be pi r square h plus 2 pi r h dr, right? And then plus dr square h minus pi r square h. Okay, so now it's clear. There's one term that can cancel each other, so which is this guy. Right, what we have is 2 pi r h dr, then plus dr square multiplied h. Okay, so now at this step, we need to recall our context. Our context that this change in the variable radius is actually very, very small. Now it's tending towards zero. So when this happens, we have dr going to zero. This is the first term. What's changing, right? The others all stay as constant. This is another term that's changing. dr square also going to zero. Now this is where we use sort of the analysis on the scale itself. So both of them will go to zero, and we want to know which one goes to zero faster. Because if it goes to zero faster, then we can ignore it because the other term is just so much bigger than the term that's going to zero much faster. So of course, now when dr is very small, for example, 0.001, dr square is going to be 0.00001, right? So anything when the dr is taking a very small value, then this the second term, the dr square, is always going to be much smaller, right? Much smaller. So now this gives us a conclusion that when now this dr goes to even smaller, right? More zeros. Now this term will approximately equal to zero, right? Because it's going to be doubling the same amounts, right? So squaring the same amount. So basically that means that it will go to zero much faster. And that also means that when they are very, very different in terms of scale, their order, then we can just ignore them, right? Because ignore it because it's so small that we can basically ignore it. So that means we can approximate this equation, this expression as 2 pi r h dr, right? So dr. Okay, so now this is our conclusion here. And what this gives us is that dv equals to 2 pi r h dr. And if we move dr to the left side, what we have is 2 pi r h, right? So which happens to be the same as our analytic derivation, which is 2 pi hr, right? So basically what this tells us is that even if we go through these routes of analyzing the differential in volume, we have the same conclusion, which is that our sensitivity of volume with respect to change in the radius is actually the same expression as if we were to use the derivative rule itself. All right. So that's about partial derivative, and it also gives us an idea, right? When we are faced with multiple variables who are all changing, then how do we know which one do we need to invest in to act upon, right? So as to get the biggest increase or biggest improvement in our projective, which is the volume in this case. All right, so next topic is the continuous function. So a continuous function literally means that the function is continuous from this one, right? So that means that a function, I can draw the function on the screen without lifting my pen. So if I happen to lift my pen, and then there's another function here, right? So meaning this does a break in this function, and it's not continuous function. So not continuous function also include examples like, for example, this function, right? Because this one is on the left is going towards very big, on the right is going towards a very small. So there's a breakpoint in between. So there's also a discontinuous function. It can also be like this. So that function, and then suddenly there's a circle. So meaning at this point, right, is not continuous. And we see that this whole function is discontinuous, right? Discontinuous. Now, if you want to be more specific about the continuity across different ranges or different points, right? So for example, this is x equal to c, right? We can actually be more specific. So this function, for example, this function is f of x. It is only discontinuous at this specific point, which is x equal to c, right? And all the other points is all continuous, right? So we can say that. So this is what I can say about this function, although it is a discontinuous function, but we know that this is the only point that is discontinuous across the whole domain of the function. Then we can say that in all the other regions of the function, right, it is continuous, right? Then we can actually be able to do something else if it's continuous at least at all the other points. Okay, so other examples include, for example, f of x equals to 1 over x minus 1, right? So when we are presented with this function, we know that the bottom, the denominator cannot be 0, meaning x cannot be 1, right? So what happens if x equal to 1? So if x is equal to 1, that means we have 1 over 0, right? So this is something not defined, right? If it's not defined, then meaning the value of this function does not exist, right? So f x equals to 1 or f of 1 not exists, right? So it does not exist. So meaning it is not continuous at this point because there's no value, because this is a math error, right? However, x can be any other points like 2, 3, -5, or the other points. It is continuous, right? So this is what you have about continuous function. And this is a very good property, because now if it is continuous, then what we know is that the limit when x goes to c for a continuous function is just the value at this particular point, right? So this is the function value, and it happens to be the limits when x goes to this point, c, right? So this is if it is continuous at this particular point, meaning x equal to c, right? And then we can just use this property. So that's a nice property to use. Okay, now more expansion on the limits. So a limit is actually sort of can be thought as another operation, another function, right? So previously we have y equals to f of x. Now what happens is that x is our input, right? And y is our output. So limit is actually a function, right? So it's an operation. Now, when we say limit x go to c for the function f of x, right? What this means is that now my input is actually f of x, right? We are looking at this function. And also we have x goes to c. So this is my two inputs, right? So I have two inputs. And my output is the value. What is the value of this limit when x goes to c, right? So this is my output. This is output. So what that means is that we need to have two things. First, which value the x is tending towards, right? So c can be 0, can be 1, can be even infinity, right? So so this is one of the inputs. It is a context. It is a condition we must have, right? And it's only specific to a particular point or infinity. And also which function we're talking about, right? So this is our subject of interest. And then this is the value of the limit. So so that's how we can interpret the limit itself. In the case of, for example, the previous example, when x goes to 1, we have x minus 1, right? So what happens is that x, as we know, cannot be 1, right? So if it is 1, then the function value of this function of interest does not exist. So by this argument, we can see that the function is actually itself is not, the limit does not exist, right? So limit not exist, because we know that when because x cannot be 0, and if it is 0, then it's going to be 1 over 0, right? So which doesn't exist. So that's one case. However, if we say limit x goes to 2 of this function x minus 1, now because we know that the function, which is this one, is not continuous only at this point, which is x equal to 1, right? So because x cannot be 1, which means that in all other points it is continuous. Now, if it is, then we can just plug in to the value of x equal to 2, right? So we can just say 2 minus 1, which is negative 1, right? So this is the limit. And we can actually be more specific, because limit now is actually an operation. So the operation, when it needs to be sort of applied to each element in the function. So I can say, in this case, the only change element is x. So say x goes to 2, right? So limit of x minus 1, because now the limit sort of moves inside each element. And then for the constants, their limit is just themselves, right? So you can say that this guy will be the value of 2, because x is going to 2, right? So that's another case. So there's one more case. So for example, for this function, right? For this function, when x, so although the function is not defined, for example, this is 2, right? So x equals to 2. So meaning the domain, x cannot be 2. But what is the limit when x goes to 2 for this function, f of x? This is f of x. And graphically, we know that this function, if x tends to 2 from the left, which means x tends to 2 from the left, graphically it means tends to 2 from the left, and then tends to 2 from the right. This tends to 2 from the right, right? What means so graphically, when we know that the value of the limit actually exists because they are equal to each other, right? So they actually will converge, will overlap at this particular point. So if imagine we have another line overlap, and then they will actually be this the value will actually be the value of this function at this point. So they'll be equal to each other. So meaning there are cases when even if the function, the domain is not define at this particular point, the limit exists, right? However, if say there's another case, it's like here, and moving on, this is a circle, and continue from this point, right? So this is one of the questions in this week's option exercise. So meaning this function increases, and then if we go from the left, we'll arrive at this point. If we go from the right, we'll arrive at this point. So they are not equal to each other. That's why we need to say the limit does not exist, right? So analyzing from the left and the right limits is necessary when, for example, at the point when the function is not defined, right? So that's when if it is continuous in terms of the function itself, then we can just plug in the limits, and then for example, in this case, we just plug in, so then gets the value of the limit. All right, so I think that's about it. And thanks for watching the video, and hope to see you in the next video. Thank you.